means that if x is in that interval centered at a, with half with r, then this sum makes sense. Therefore, you can really sum it, and whatever that sum is, which depends on x, and we give it a name. It's called f of x. So that becomes a function of x. And then the assertion here is that then f is differentiable, therefore continuous as well, of course, because it's differentiable. On that open part, the interval convergence could be closed, could be open, could be half closed, half open. All right, but here I'm saying that if f, if f stands for this, then f is differentiable on the open part. Forget about the endpoint. I don't care about what happened at endpoint. Perhaps the original function converges, perhaps it doesn't. Right, but I don't care. I focus on the open part, and within that open part, f is a nice differentiable function. And furthermore, since it is differentiable, that means you can take derivative, and that derivative function is once again a nice function in that it is a sum of another series, and this series can be easily obtained by simply take this one and naively differentiate term by term as if you are dealing with binomial. And that's extremely good news. And because it's continuous, therefore, because it's differentiable, and therefore it's continuous, and therefore you can take antiderivative, right? And by fundamental theory calculus, and so you can talk about this one is antiderivative, and of course it's not unique. It's up, there's a freedom where you can add an additive constant, right? So that constant term is called a C. But other than that, you simply take the original one and then integrate, or taking antiderivative term by term. So I'm going to cast it in this form. Term by term, antiderivative. And moreover, in the radius of convergence of 1 and 2, the series in 1 and series in 2, this right-hand side, are both equal to exactly that same radius convergence of this series that you start off with. So are both equal to 2. And I should clarify, even though the endpoint behavior, may be different. For example, it could be that the original series, it happens to be closed interval, right? And as you take the derivative, perhaps it's half closed, half open. That's possible. So I'm not claiming that the details will be the same at the endpoints, but I'm claiming at least the open part. The interval size is the same. The only difference, possible difference, will be at the endpoints. Right. So even though the interval of convergence may not be exactly the same. But if they are different, that difference is only in terms of the endpoints. For example, one is from let's say -4 to 4, open, and another one is from -4 to 4 but close, open. Something that the only difference is at most that. Okay, so this is the big theorem. It's extremely good news. It essentially tells you the message that, first of all, if you have a power series, within the interval convergence, you sum it, then it results in a function called f of x. It is extremely well-behaved function. You can take derivative as many times as you want. Why? Because first of all, it says that it's differentiable once. But as soon as it's differentiable once, since it also tells you that that derivative is, once again, of this form, is a sum of power series, and therefore you can do it again. So you can take derivative as many times as you want. You can take antiderivative as many times as you want. Okay, so it's a very good function. And then secondly, as you do this derivative, antiderivative business, you can this power series behave the way that you would naively expect. So this is extremely good message. All right, and then I also recall last time. So last time we start with. Last time, we start with just one case, and that is 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x squared, and so on. So geometric series, this power series. And so that power series, radius convergence is equal to 1. Okay, and interval convergence, intervals of convergence is, must be from negative, well, it's centered at 0, so it must be from negative 1 to 1. But if you plug in 1, it doesn't work. So this end is open. If you plug in negative 1, it doesn't work either. That, right? And then from that, we manage to create many examples. So here are some examples. Let's say, suppose I have 2 over 3 minus 4x. Then you simply manipulate it. Is this a sum of a certain power series? Well, yeah. One way of doing it is this. For example, here is a. If I ask you to express this as a power series centered at 0, then what would you do? Well, this is 2 over 3, 1 minus 3x over 3, right? And therefore, this is 2/3. Essentially, I'm still using the geometric series concept. So this one would be a geometric series with leading coefficient 2/3 and with common ratio 4x over 3. So therefore, I get 2/3 plus 8, 9, x plus 16 times 2, 32 over 27x squared, and so on. So that's a power series right there. Second example, if I may erase this. Second example, express once again the same thing, which is 2, 3 minus 4x as a power series centered at for no particular reason, centered at 1, then how can I manage that? Well, in other words, I want to write it a power series in x minus 1. Is that right? Something like C0 plus C1 x minus 1 plus C2 x minus 1 squared and so on. All right, so power series in x minus 1. So I might as well just temporarily name it, just to ease the notation, the presentation. I'm going to call this U. And then, therefore, you can re-express x in terms of U. That would be x is equal to U plus 1. It's just a strategy. You don't have to do this, but this is a nice strategy for you to manipulate the expression. So we have something like this, and then you see that this is 2 minus 3 minus 4 U plus 1. And with this, then this is written as negative 1 minus 4U, and therefore is negative 2 over 1 plus 4U. And therefore is a geometric series with leading term negative 2. What is the common ratio? If I think of this as A over 1 minus R. So what is A? Negative 2. Yeah, negative 4U, right? So negative, leading term is this. And next one, so A is equal to negative 2, R is equal to negative 4U. So it's going to be alternating, right? So plus 8U, is that right? Okay, and minus what? 32U squared, right? Plus 128U cubed minus, etc. In general, if you want to make it very clear, then you go n goes from 0 to infinity. And in terms of sign, it is negative 1 to the nth power. In terms of the this one, you always have a 2 there, and times 4 to the n minus 1 power, and then u to the nth power. Oh, I'm sorry. This is 4 to the nth power, actually. 4 to the nth power, and times always they have this factor of 2, right? And each one you have extra power of 4 and extra power u. And so this is, therefore, n goes from 0 to infinity, negative 1 to the nth power times 2 to the 2n power plus 1 power, 2n plus 1, times, what is u? U is what? X minus 1. So I re-express in terms of x to the x minus 1 to the nth power. So this is the power series centered at 1. Right? Power series centered at 1. In other words, the power series of x minus 1. So the same function, I can decide where, in which neighborhood, around which number, around which position, I'm going to express it as a power series. Same function, right? But I can do this business around x equal to 0, or can I do it around x equal to 1, or x equal to 0.5, whatever you can do.
How do you bring the 1 plus 4u up?
Which step?
Right here. Where
Here?
Yeah.
I multiply top and bottom by negative 1, right? Okay, so this becomes negative 2. This one, both term flip
Why?
side.
After that, why?
After that, because you see that this is of the form a over 1 minus r, right? A being negative 2, r being negative 4u, right? And therefore, this is the sum of geometric series. All right, so this is first term. Second term is the first term multiplied by the common ratio negative 4u. Right, so this becomes positive 8u. And next term